I'm going to introduce, we have Tim Hudson and Dr. Paul Dale giving their presentation on OpenSSL 3.0, Accelerating Forwards. If you can give them a big, warm welcome applause, guys.
Up on the stage, so.
You has the power.
Oh, I get the clicker to start with.
Oh, you're starting to
Oh,
talk.
great, can't see a thing. So what we're actually going to do, and I'm not going to bother to read out our abstracts, you've got an idea of what we're talking about. In essence is a whole pile of the changes that have happened in OpenSSL over the last 12, 14 months or so. So I'm just going to launch straight into it. And one of the things that we always feel is a good thing to reflect on is, where did OpenSSL come from? And it's a history that a lot of folks here probably are aware of, but when we talk about OpenSSL overseas, very few people seem to realise that it originally came from something fairly local to here. So the origins of OpenSSL actually were in 1996 up in Brisbane. And it was just two people, and between them managed to produce about 100,000 lines of code. Now, if you forward fast about 23 years, OpenSSL is now 17 people and about 400,000 lines of code. So it's gone from two people working on something to a group that's distributed all over the place. And we recently celebrated the official 20th anniversary of OpenSSL. That was in late December last year. And that's with the project itself existing. So it's been around for quite a while. There's a whole new generation of people who have just sort of never known the concept of not being able to have access to a full-strength cryptographic toolkit worldwide. So that's something that we're pretty focused on in terms of being able to provide. If you have a look up here on this slide, this is the current set of OpenSSL Management Committee and OpenSSL committees. So in essence, this is the project governance team and those who are responsible for checking code into the repository. And in OpenSSL terms, we separate the two concepts out. So those who are interested in supporting the longevity of the project and making sure it's maintained over time, looking at things like funding, direction, etc. We form a management committee, and there's a number of us involved in that. The project itself has formal bylaws, but the more important thing that we've done over the last 4 years or so is broaden the number of people who have the ability to review and commit code into the OpenSSL repository. And I've done a little breakdown the bottom there so you can get an idea that there's no one country that dominates OpenSSL in terms of contributions. We've got people from all around the world contributing. And when you have a look at the geographical regions, sure, there's still a whole focus in Europe, and that's simply a reflection of the times and the history behind the project, and the fact that there's a lot more concentration on the importance of privacy protection and the underlying cryptographic algorithms and routines that are necessary to protect that. So from that perspective, we're feeling fairly reasonably resourced in terms of the number of people and the locations and what we're able to do with that side of things. And the other thing is, because we're sitting out on GitHub, we don't have to go and produce statistics ourselves. We simply click on the little icons and we can see what our project history is. So the top line there is basically the commit frequency over time. And you're able to see that effectively when the project began, there's a bit of activity and then kind of a quiet period, relatively speaking, in terms of contributions. So there's a 10-year period in the middle there where not an awful lot was going on. And then in 2014, we started to reinvigorate the project, get more people involved, take on more work. More people means you can do more things. Do more things means you can support more concepts, adding additional capabilities and things along those lines. And if we have a look at the most recent 12 months of the history of the project, which is the lovely little orange bars at the bottom there, you can see that, and this is on a weekly basis, you can see that in essence we're looking at somewhere between 25 and 45 commits per week. So there's 5 to 8 commits per day, and that's the sign of a reasonably healthy project. So there's a lot of folks contributing. We're not sitting in a state we don't feel the job is done. A whole pile of additional work's going in, and we've got a very active community participating in it. The other thing you could notice is the project team, we do actually take a break over Christmas. There's a couple of days there where the commit rate drops down, but it doesn't go to zero. There's still people who work through the Christmas period. And the big blip you can see in the middle there, that's when we changed across to the Apache 2.0 license, and that hit a whole pile of parts of the code. And then if we turn around and look at the project activity over time, so those first two graphs were showing the commits into the project itself. How do we go about measuring how people use OpenSSL? So who's not actually contributing code but working with it? And there's a couple of additional graphs you can get out of GitHub, and that's looking at the number of clones. How many people have cloned the repository? How many of those clones are active over time? And having a look at those sorts of statistics gives us a sense of what people are doing and what people are working with. And if you have a look at it, we can also get visitor statistics. So GitHub lets us see how many people are coming to look at OpenSSL on GitHub, so looking at the code, as distinct from looking at the project website where we talk about documentation and things. What are people doing with the code itself? And those stats on the bottom give us an idea of how people are looking at things, and this is just over the last couple of weeks.
Okay, so now you know the people who are involved, some idea of what the management's about. We'll get on to what the project is you know, what its current status is. The main focus at the moment is on transparency. We're trying to do all our development out in the open. We're attempting to see most of the decisions that are being made, so get external visibility, open the project up to the world. Yeah. Anyway, there are just some points. We have a FIPS project, there's 5 sponsors. We have an architecture document, that's where we want to be. We actually have a plan of this is where we're going to get to. I think Tim covers that a bit later. We've got a design for the 3.0 release, which I don't think's in this, but bits of it will sort of flow through. And we have a very large number of pull requests that are just coming through continuously. We're sitting at somewhat over 200 at the moment, and yeah, the number seems to be increasing, not decreasing. Now, the next version of OpenSSL is going to be 3.0.0. So the current version is 1.1.1. We are jumping to 3. There was a long discussion about this, and it really came down to, we have a FIPS 2.0 module already. We don't want to do an OpenSSL 2.0 module that won't work with it, so we'll just jump to 3. And as part of this, we're also taking on almost semantic versioning, where there's a couple of complexities in the way we support old releases that mean we can't do precisely semantic versioning, but it will be very close. And as Tim mentioned, the Apache license will apply from 3.0 and future releases. Okay. The 3.0 project, our goal is code complete by the end of this year. So that would be a beta level code. Submission to the FIPS labs early Q2 2020. Maybe a bit fuzzy on that date, but that will also correspond with the official OpenSSL 3.0 release date. And FIPS validation 6 to 9 months after is normal. So if you're interested in FIPS, there's a gap until 2021 basically. But otherwise, that's the timeline. It's looking good so far. It's probably going to be missed, but these things are.
Well, you have to have aspirations, you have to have a goal. And one of the things we're also trying to improve in the project is to let people know what we're working on before we start working on it. And it's quite a change in how we've operated. In the past, you found out what was going to happen in OpenSSL after the code had already gone in. Now we're discussing the sorts of changes. We're looking at what we think needs to change within the actual code base itself, discussing it in a much broader community, seeking a wider set of views, and having the discussions of the pros and cons out in the open. And we found that gets your community much more engaged, but it also leads to better decision making in general. And that's something that we've been working on improving from the governance side of things within the project. So what's our drivers in terms of what we're working on for this release? And the important thing that we're looking at is whenever we change something, we break things for our users. And breaking things for your users is a great way to get some really positive feedback from your user base. If you break something, people will tell you. So one of the things that we looked at is what was causing the breakage, what's causing the pain, what's causing us all of these issues. And we sat down and figured out that we simply had to make a transition where we got the applications using OpenSSL out of the internals. We had to turn around and basically get that separation. And that was the big major change we made in going from the 1.0 series to the 1.1 series. We made the majority of the data structures opaque. And what that meant is we then become free to change the internal implementation structure. We noticed the whole pile of error handling is somewhat inconsistent, and it's inconsistent because we'd never documented the policies of, APIs need to return errors in this manner. It was simply the person working on a section of code did the error handling that they thought made sense. So there's lots of little inconsistencies that we're tidying up over time. And things about who owned the memory. Did the library allocate the memory? Did the application allocate the memory? Who's responsible for freeing it? We had to turn around and look at all of these things. And in essence, these are the major areas that break applications. And we think we can do a better job going forward in terms of handling that. So, in essence, by making everything opaque, and there's one exception to that, the ASM1 handling routines remain non-opaque simply because it was too big a chunk of code to tackle, and adding more documentation and improving the testing, we should be able to get to the state where we make different mistakes in the future. So the definition of stupidity, keep doing the same thing expecting a different result. Well, we want a different result. We want less pain in the user base of OpenSSL. So we're trying to tackle things in a slightly different manner going forward. So the other thing that we did is we didn't go and take a silly approach of looking, okay, I've got the structure, it's got 12 fields, I need to put an accessor function in for all 12 fields. We actually made a value judgment on what we thought made sense for people to access. We didn't want to provide complete access to everything because our plans were to change the internal structure. So if the internal structures are changing and we've created an accessor for every field, we haven't solved any problem. So we turned around and basically said, this is a subset of what we think makes sense conceptually independent of the implementation, which meant we knew we were leaving gaps. We knew there were going to be some people say, hey, I'm using that field, I need that field. But we made a conscious choice to do less than everything up front to get the feedback from the vendor community. And this was the pain and the transition of going through 1.1.
Okay, not all OpenSSL users use the APIs at the same level. We have low-level APIs where you just call the raw crypto function and do all the rest of the management yourself. We have higher level APIs where a lot of that's taken away, and it's a black box that does this piece of crypto. Some capabilities are only available at the higher level API. Some are only available at the low level API. So there's a real mix and match of where things are done and how they can be done. Sometimes you can do it low, sometimes you have to do it with the low level API. So, we have a mess in the APIs. Okay, so how are we addressing that? We're changing to only using higher level APIs. The low level APIs over time will disappear. The higher level APIs will gain the functionality they need to do what the low levels did before. The higher level APIs will have a consistent error handling because they're new, we can define this. Some of the low level APIs return a void. You don't know if it worked or not. It just ran. So yeah, consistent error handling. Likewise, consistent use of memory allocation. The thing that allocates the lump of memory is going to be the thing that frees it. It's not going to be deferred somewhere else. And yeah, the last one, checking error returns. There's a surprising number of cases where that doesn't happen. Okay, to do this, there's a number of challenges. OpenSSL has a lot of old code. It supports a lot of old platforms. It supports more platforms than we really know about. You know, does anybody use PA risk? Any show of hands? Yeah, I knew there'd be one. There always is. Okay, that was PA risk was stopped manufacturer support, what, 20 years ago? And it's still in OpenSSL, it's still there. We want to be able to get rid of all of this old code, but we can't get rid of it because people still use it. So we're in a sort of a bit of a quandary there. Okay, we hit the same problem for platforms that we do for architectures. At least in this case, we have got a policy. We have a multi-tiered list. The primary tier is the machines that people who work on OpenSSL use personally, typically Linux. If there's a breakage in that, it will be discovered within minutes. The secondary is the platforms officially supported by the OpenSSL team. That's quite a larger list. It includes Windows, it includes AIX, it includes HPUX, VMS. So it's quite a wide list. The expectation there is, if there's a problem introduced into that tree, it will be found, you know, within a few days to a week, and certainly would be found before a release. The next tier down is community platforms, which is other people's have weird machines and they'll file bug reports. You know, we do try to fix them, but again, they're a lower priority thing because testing them is really hard. And finally, the largest group are the ones we don't know about. There is definitely more machines we don't know about than we do, which is, yeah, makes some of this planning difficult. Is that a Tim?
Thanks. So, you know, as Paul mentioned, the largest group of platforms is the unknowns. And it's not that we don't know that it doesn't work, it's that we don't have anybody that's willing to turn around and say, if a problem comes up, I can help you work through the issue. So we're being a lot more transparent about the things we know versus the things we don't know, so people can make their own value judgment. And we found that if we tell somebody, hey, you're in the unknown category, occasionally a vendor will come along and say, how do we turn around and you know, get us into the supported list? And that generally involves, you know, provide us an environment which we can add into our testing. So if we can test it, we'll detect it, we'll be able to have access to the platform, we'll be able to fix it. But if we don't have access to the platform, we simply don't know how it's going to turn out. So one of the things that we've noticed when we sat down and analysed the entire code base is the biggest problem that we actually have is how do we go from I'd like to perform this algorithm through to finding what its implementation is. And we turn around and analyse through the code base to have a look at the number of different ways we do it. Now, the answer is actually 8. There are 8 different ways in which we can perform algorithm selection, which is probably 6 too many. And we've turned around and had a look through that and looked at all of the different approaches of how we can switch code. And one of the reasons is why we focused on this, because code switching and the ability to get to algorithms is pretty critical in the library itself. And when we've got multiple ways of handling the same underlying concept, it's an opportunity for us to introduce different behaviours, different bugs, different outcomes for the user. So it's also the place where people want to be able to extend things. I want to be able to turn around and say, hey, I'd like to add an algorithm. So if you want to get yourself a series of pain, try and add a new algorithm into OpenSSL. You have to touch a whole pile of code in a whole pile of places. It shouldn't be that hard, but it is that hard simply because we never designed to make this easy. Right? If you don't design to make something easy, you'll get the outcome that we currently have. So basically, we're not operating as a framework. We don't see ourselves previously as a cryptographic framework environment, We saw ourselves as an implementation of a set of routines, and extensibility wasn't an objective. We also don't have the concept of dynamic discovery. So when OpenSSL starts up, it knows everything that exists. There's no concept of somebody could plug some hardware in with additional capability. The APIs and the architecture just aren't designed to handle that. So what do? We've got all of this code that does similar things. Simple solution would be delete some of it. Get rid of the code. If we delete it, we have less code to maintain. Oh, it must be more secure because there's less code. And believe you me, that's been a consistent argument within the actual community itself. I personally don't use the VMS platform, so why are we carrying around VMS code? Let's get rid of it. I'll feel safer. And the counter argument is, well, you're not using VMS, so if there's bugs in the VMS code, you don't really care anyway. Some other people are. And when you've got a community that's got such diverse interests and diverse requirements, it's really hard to actually make the decision to drop something. So what we turned around and looked at is maybe we could push some of the unusual code out of the repository, get somebody else to maintain it. Is it feasible to do that? And when we figured out that if you push code out of the repository because of OpenSSL's internal structures, you still need to leave knowledge of that code's existence behind for things to work. And that's not a particularly good environment. And then we turned around and had a look at how we'd handled FIPS and how we handled engines. And we turned around and had a look at those and thought, maybe we can do a better job.
Okay, FIPS 140. Brings fear into the hearts of programmers. If you don't know, it's a standard of well over 10,000 pages of documentation. It's not internally consistent. There's arbitrary rulings that just go, why did they do that? That just doesn't make sense. And you're expected to follow it all. It's fun. In the old OpenSSL, so 1.0, it had two ways of linking the FIPS module. This is the static way, so it built a FIPS canister, which is then linked into the application, and it's all sort of one blob. The shared library way, you still built the FIPS canister, but you linked it into a shared libcrypto, which multiple applications could then share because it's a shared library. The current project is not following either of these paths. We're still using the shared libraries because it's the more commonly used version. We're having a separate shared library that is the FIPS module. And then libcrypto will load it, and then that application will load libcrypto. Now, still in version 1.0, FIPS was invasive. What is it? Almost 200 hooks. This isn't the FIPS module, this is the mainline OpenSSL source code. These are the changes that were necessary to work with the old form. So it's 200 hooks, almost 700 symbols. It had to rename symbols so you didn't get symbol name clashes. Had to change function names anyway. And the whole FIPS canister had to be self-contained, so you ended up with lots of duplicate code where, oh, FIPS needs to do this, let's pull that into the canister, etc., etc. Basically, a horrible, hard to maintain mess. I think that sums it up. Now, beyond the library, OpenSSL ships with some applications. They needed to change as well. The main application, checking an environment variable to say, am I in FIPS mode? Yeah, that's perfectly reasonable. I'm happy with that change. A PKCS12 app needing to change because of FIPS? That's just, FIPS doesn't do PKCS12, so. And if you especially note the old cipher it was using, a nice export quality RC2, everybody's favourite. Yeah. So, and all the low-level crypto routines, they needed to be patched because you could still call the low-level routines. They had to they just had to return an error basically, but every single one had to be patched. Even the EVP routines, which is our nice interface, had to be patched to support FIPS. It was, yeah, a mess. what are we on here? Yeah. And also in the library, different components. Again, PEM. Why do you need FIPS changes in PEM? Why do you need FIPS changes in PKCS 12? It's just, FIPS doesn't go there. The RAND, I can understand FIPS does talk about random number generators, so that's plausible. But these changes are just huge and widespread. And Tim will actually run through some code just to show you how enjoyable it is.
So, this is meant to be a technical presentation which obligates us to show code. I believe that's the requirements of the AusCERT program committee. So one of the things we did recently, we actually got together as a group to wander through, in essence, the mistakes of the past. That's what I like to refer to them, is what did we do to get where we were? And we turned around and had a look, and we basically said, how does all the FIPS code work? And we wandered through and looked at every single place where we had to make code changes. And we started at the beginning saying, hey, how many people in the group think the FIPS code's evasive? And people thought, yeah, it's ugly, but it's not evasive. But when we sat down and did the analysis, nobody was happy with the approach that had been taken. So if you have a look at the current code base, so if you look at the 1.1 code base, all of this code's gone.
Okay, back to the other secret in the hole that tries to keep buried. The engines. The engines they're a good idea. If I have a piece of hardware which I want to plug into my machine and have OpenSSL use that hardware for something, the way to do it is use an engine. That's what they were designed for. Again, this requires the ability to dispatch, because you've got to intercept a dispatch normally and redirect it to an engine. Again, it's not as invasive as the FIPS changes. There's a lot less of them, but they are in all sorts of places they shouldn't be. If you look at the list of the engine interfaces there, it's in the EVP key methods, which is all the public key crypto, but it's also in the low-level RSA methods. So it's actually got 2 points of dispatch, and they both actually are important. And code review.
And if we have a look at it, you can see the code changes. Again, they're in lots of different places. They wander through lots of parts of the code. Now, this code is still in the current master. It's still in the 1.1 release. And the hooks are kind of all over the place. And we think we should be able to sit down and figure out a different way of doing it. We shouldn't have two mechanisms for handling the same issue.
Yeah. So what we have two mechanisms that are both attempting to dispatch in different ways. The engine is talking to hardware. The FIPS is talking to algorithms, but also preventing you using algorithms you're not allowed to. They're both dispatchers, and they were both sort of just hacked into the code base in different ways, and they interact, and there is quite a mess there. Okay, so the challenge we had was we need something different, something that is extensible. So if somebody has a new algorithm, they can add it without touching the main code base. It has to be something that switches implementations, because that's what we're replacing. It really needs to be a superset of what the FIPS and engines can support, so we can get rid of both of them. Yeah. So the solutions, oh, mine's gone blank.
Step one, admit there's a problem.
Okay, yeah, step one, admit there's a problem. Step two, try to find the problem. We've admitted there's a problem. Now we've got to work out, well, we had to work out what we can do about this. We need something that replaces both FIPS and engine. We need, again, the extensible, the switchable superset. Is that you?
Yeah, so at this stage, what we sat down and did is figure out, and we've still got a whole pile of slides to go, so we'll speed up on some of the material here, is we need to design a new selection mechanism. So we've got to be able to do it. And the approach that we've done, if you looked at the earlier slides, This is what we affectionately refer to as pink nirvana. One of the guys chose to draw the diagram in pink for no reason that I could fathom. But in essence, we're going to reorganise everything. So you see down on the bottom core section, sitting in the middle and sitting on the right-hand side, you can see a set of providers. So in essence, we're going to gather the implementations into providers and then change the mainline code to be able to find the implementations through a consistent mechanism and a consistent mean. And the idea is we're going to do this without irritating our user base. It should be as simple as when you get the 3.0.0 distribution, you take your code, you type make, you're done. It's finished. One recompile and nothing breaks. Now, that's assuming you've made it up to the 1.1 release. So as long as you've made it to 1.1, the 1.1 to 3.0 transition, we're aiming for it to be painless. And internally, our switching logic is kind of a bit like this, and that evolves over time. As we're sitting at about 5 minutes to go.
I will do properties really quickly. Okay, the fundamental switching mechanism we're using are called properties. They are human readable, comma separated ASCII strings. They're designed to be simple, flexible, so they've got to be able to do everything we need, and they have to be efficient because we're going to be doing a lot of this. So a property definition is a comma separated list of name equals value pairs. Names aren't case sensitive, although we're going to set a guideline, use lowercase. So in the current libcrypto, all the algorithms will fall into one of two categories. They will either have a property default equals yes, which means they're from the default provider, or they will have a property legacy equals yes, meaning it's an older, weaker algorithm. And this gives you the ability to just say, I don't want any older, weaker algorithms by saying legacy equals no. And the FIPS provider will also have its own setting. Third-party developers are allowed to define their own properties. The only thing is we've reserved all the names that don't have a dot in them. So a third-party name must have a dot, which gives you it gives you a naming hierarchy essentially. So you could say Intel dot blah, and that's an Intel property. A couple of examples. The top one saying, I want FIPS, I want whatever that x86.optimized is. The second line is actually saying the same thing, because if you leave out the equals yes and just have a name, the equals yes is assumed. So we've got a shortcut for saying I want it, no shortcut for saying I don't. Queries, again strings, comma separated. They are either equality or inequality tests, and they can have a leading question mark, which means optional or preferable. So again, some queries. There's an optional there. We'll skip over that. I've got some railroad diagrams of the syntax, which I probably don't have time to talk to, so we'll just skip through them. They'll be in the minutes when we're done. Changes file.
So we've got a whole pile of changes that have already gone into 3.0. So 3.0 is not something that's, we're talking about doing something maybe in the future. We're actually probably about halfway through the engineering work involved in the release itself. So this is just a pretty simple, straightforward summary out of what's sitting in the changes file as it currently sits. We've added a new API for Macs. So, CMAC, GMAC and HMAC were all driven differently. So we've now got a new API for it. And it kind of looks like this. So this is us driving CMAC. If we flip through to what HMAC looks like, you notice basically 2 lines changed. So CMAC's got a cipher underneath it, HMAC's got a digest, but the user's mainline code remains the same. That's not currently true in the 1.1 code base, but for 3.0, you've got a much nicer API. Same things for KDFs. There wasn't a key derivation function API, so HKDF, PBKDF2, SCrypt, TLSPRF, they're all handled differently. Well, now they all pretty much look the same. The parameters may be different to go into setting up the functions, but the way you drive it is equivalent. Okay, here, just to show we've got some activity, it's pull requests that basically revolving around this project. All the red ones are the re-architecting, redesign work. So we've got, I think, quite a lot of them. Most of the not red ones are FIPS work. So
Yeah. Okay, so we're re-architecting. The anticipated benefits are that, you know, we'll be able to pull crypto in from anywhere. People can write their own crypto and we can use it just transparently. Internally, we will only have one switching mechanism, so it'll be cleaner and more maintainable. National algorithms, like the Russian GOS suite or the Chinese SM suite, they can do their own provider and just plug it in. So it gives us that. Yeah, and in the future, PKCS 11 is on the cards. Target dates, intending to be code complete by the end of this year, release early to mid next year. And the key thing is, most applications will not have to change a line of code to get the benefits. Questions, if we've got time? Good.
Quick one. So would the third-party... So would the third-party providers that you mentioned, for example, the Chinese version of encryption, would there be opaque as well?
They can do whatever they like inside.
So it's not, the code wouldn't be visible in the OpenSSL, would it? In terms of, would you make it opaque, or it's just totally transparent? Oh, totally hidden from everybody
So
else?
every third-party implementer of a provider will be able to make the choice as to whether or not they publish their code. So we're providing effectively an ABI into the providers, which will enable third parties to either add open source componentry or not. We're not making a policy decision on that ourselves, but of course everything that OpenSSL ships with is always in open source form.
All right, guys, we'll end it there. If you can give them a big thank you applause.
Thank you.